Chapter 5 has to do with maxima and minima and in general optimization. So that is finding these maxima and minima. So go ahead and read through this first page and feel free to pause at any time, of course, to take the time to think about these ideas. So one of these studies actually uses health tweets and Google searches. Notice this correlation with the actual positive confirmed laboratory cases. So you can see the correlation here between the different colored curves. But we're going to use this as an example to motivate why we would care to find maxima and minima of a function. As we've seen previously, these sharp edges, these sharp peaks and valleys tend to cause problems in terms of taking derivatives. So we want a nice example, so we'll just smooth out that function. And you can see on the next page here that we've smoothed things out, and we'll just start off by reviewing what we learned before about derivatives graphically. So remember that when you want to plot a derivative, that what we want to think about is the graphical interpretation, and that is the slope of the tangent line. So the derivative at a point, remember, is exactly the slope of the tangent line. So that means if we take different test points and sketch tangent lines, so I'm taking 1.5 here roughly, then the slope of that tangent line represents the value of the derivative, and we have a test point for our derivative plot. So I notice that my tangent line at 1.5 has a slope of 0, and so I plot a height of 0 on the derivative plot. Now peaks and valleys are good test points to take. So I've taken one at this minima at 1.5, and I'll take another test point at 3, roughly 4.5, and 5.5. And that's because I can very quickly notice, the more of these I do, and the more tangent lines I draw, notice that at every peak and valley it turns out that the tangent line has a slope of 0. So these are always, our eye is drawn to these peaks and valleys, and these are always easy points to grab. So I'm just plotting these heights on my derivative as 0 heights. Now what you can notice is that after you've taken these test points, you split your domain into a few different subdomains, and the function is strictly increasing or decreasing on each of these subdomains. So starting from the left, we can just take any point in that subdomain and notice that while the slope of the tangent line varies, it doesn't change its sign. So that is to say, this function from 0 to 1.5 is decreasing on that entire interval. Equivalently, the slope of the tangent is negative. So just by taking one test point, that's enough for us to see. And I'll just go ahead and fix my derivative plot real quick, because I marked that the derivative was 0 at x equals 1 here, which is not true. So I said one thing and wrote another. So let's just fix that. So we said that the derivative was at 1.5 was 0, and that the derivative at x equals 1 was negative. So we make some mark below the x-axis. Similarly, looking at x equals 2, we can just rinse and repeat and draw a tangent line and see that that has a positive slope. So that is to say the derivative is positive at x equals 2. So we just continue along. We'll take another test point, let's say at x equals 4, sketch a tangent line, and that's a negative slope, so we mark a negative derivative. And lastly, well, not lastly, we have 2 more to go. At x equals 5, the slope of the tangent is positive, and we'll do 1 at x equals 6, that's negative. So we mark those test points, and now we have enough to get a rough sketch of our derivative plot. So this is something we did in chapter 3, but we're going to use this so that we can think about and understand the connection between maxima and minima and the derivative. So now let's consider this information in table form. So you see here a table below, and these are the test points that we looked at. And you may just pause and consider this question. If we only knew some limited information about the derivative, let's say that the derivative was 0 at a particular point of a function. So now pretend we haven't seen the original function f, and this is all I told you, was that the derivative of f at x equals 1.5 was 0. Would this be enough to determine if you have a max or a min of f at 1.5. And if you think about that for a moment, you should come to the conclusion that this is not enough information. All this tells you is that the function flattens out at x equals 1.5. So it could be a max, it could be a min, or it could be neither. So the point of this is that we need more information. However, if we add in the information at x equals 1 and x equals 2, we don't actually need a number, we just need the sign of the derivative. So at x equals 1, we found that the derivative was negative, and at x equals 2, we found the derivative was positive. Now ask yourself the same question. Is this enough information to determine if we have a max or a min at x equals 1.5? And now the answer is yes. So you may wonder, why is that the case? Well, one way to understand this is to sketch what the function behavior is based on the sign of its derivative. Whenever you have a negative derivative, that's just another way to say that the function is decreasing. So you could draw an arrow to represent that. Similarly, a zero derivative means the function's neither increasing nor decreasing. So it kind of flattens out. And if it's a positive derivative, then the function must be increasing. So we could draw an arrow like this. So now you can think about, well, what is this tracing out? This is tracing out something that looks like a minima, right? So this is the behavior that we will always see when we encounter a minima of a function. And that is to say that the derivative will change from negative to positive. And of course, if we change from negative to positive or positive to negative, we must sweep through 0. If we fill in now the remaining information, we can see the similar pattern for maxima. So we'll go ahead and just fill in at 3, the derivative was 0, 4 it was negative, 4.5, 0, 5 positive, 5.5, 0, and 6 negative. So the reasoning that we're using is this set of relations, by the way. So this is handy to have in your toolkit. So if you haven't made this connection, so a function is increasing, is what this left-hand expression is telling us, whenever the derivative is positive. So you can read this in either direction. So this is an equivalence relation. If you remember one, then you get two others. A function is decreasing whenever its derivative is negative. And lastly, a function is neither increasing nor decreasing. Flattens out whenever its derivative is 0. So this is how I'm making this connection between the shape or the behavior, I guess, of the function, whether it's increasing, decreasing, or neither, based on the sign of the derivative. So you can continue this and notice that as we sweep through x equals 3, we're tracing out a maxima. So the function kind of has this behavior. And of course, we know the original function, so we can come back up, take a look, and see that this confirms our argument, or this agrees with our argument. So we see the same pattern for the next two zeros of the derivative. The function flattens out at 4.5, is increasing, flattens out, and is decreasing. So this gives us a way to understand maxima and minima, and as we'll see, if we sharpen this up, this will give us a way to find and classify all maxima and minima of any function. All right, so now take a moment to think about the next question yourself. Think about what we've just put together here. And I would say that the main idea is that at a maxima or minima, the derivative is 0. So that will be an important idea that we'll use moving forward. So you may have already realized that before, but in any case, that will be an important part of this puzzle. So at a minima or maxima, the derivative is 0. So you may also want to consider, whenever you kind of make any sort of statement, you should always consider the converse and think about whether that's true or not. So the converse of this would be if the derivative is 0 at a point or at an interval, do you have necessarily a maxima or a minima there? And the answer to that is actually no. So you should try to think about a counterexample there. And if you sketch a cubic function, that would be a good counterexample. You can think about that. So these places where the derivative are 0, we're going to be looking at these and using them a lot and finding them to help us find these maxima and minima. So we're going to give them a name, and these are just called critical points. So a critical point of a function is any place where the derivative is 0. So that's just a definition that we'll use, so just make sure you understand that term. Whenever you see the words maxima or minima, we're always referring to relative maxima or relative minima. That just means any maxima or any minima. You can talk about absolute maxima and minima, and we won't distinguish between those in this course in general. And then extrema is just talking about these things collectively. So you'll see all of those terms, and we'll kind of use them interchangeably. So again, just coming back to that definition, critical points of f of x, using the example above, are those places where the derivative is 0. So if we look, we already have that information at x equals 1.5, 3, 4.5, and 5.5. So if you're ever asked to find critical points, then that's what you're looking for, are places where the derivative of the function is 0. So that's kind of a two-step process. You would take the derivative if you had the function, and then you would set it equal to 0 and solve for x. So this will just be a list of points here, in this case, 1.5, 3, 4.5, and 5.5. So it may be the case that you have no critical points of a function. You may have one critical point. You could have several, like in this example. You could even have an infinite amount of critical points. So be careful not to make any assumptions. Sometimes you see 4 examples in a row, and each one has 3 critical points, and so you might start assuming all functions have 3 critical points, and that's just not true. So you can think of different examples of functions to see why that's not true. So putting this all together, we have something called the first derivative test for extrema, and again, extrema just means maxima and minima of functions, and so this just puts it together formally, and you don't need to memorize this, but this will be a nice thing to reference as you work through this test on different problems. So the first thing is to just suppose we have one of these critical points. A critical point is where the derivative is 0, so one of these places where the derivative is 0. And then there are 3 kind of possibilities. The first possibility is that the derivative is positive to the right of the critical point. So you can imagine this critical point hanging out on the x-axis, x equals c, and we don't really know where it is, but just to sketch a picture, the derivative being positive to the left of this critical point would mean that the function is increasing, right? If you drew a tangent line, its slope would be positive. A critical point is where a derivative is 0, so the function flattens out at that critical point. And then if the derivative is negative to the right, this critical point, the function must be decreasing. So you can draw this picture, and you can really understand exactly what this implies. This implies that we must have a maxima at this critical point, and that's exactly what we were understanding with our table above. So this connection with the derivative and critical points and maxima and minima. So not surprisingly, if their derivative is negative to the left of a critical point and positive to the right of a critical point, then let's put our critical point in a different place for fun. Then the function must have been decreasing, flattens out, and increasing. So you can see exactly, again, that that's implying a minima at this critical point. Not a minima, a minima. All right. And then there's a third case, right? So what if the derivative has the same sign on both sides of a critical point? This could happen in 2 ways. So if you have a critical point again, what if the derivative is positive? Again, at the critical point, it's always 0, so it flattens out there. And then positive again, so it has the same sign on both sides of the critical point. Well, you can see this traces out something that kind of looks cubic. Okay. There's another case, and that is negative on both sides, right? So you have your critical point, so the derivative is 0, the function flattens out, and what if the derivative is negative on both sides? Then you have this, it also looks kind of cubic scenario, okay? But in both cases, or in either case, you have neither a max nor a min, okay? So let's just summarize that. Okay, so again, that's our test, and we can use this as a reference, but we don't need to really memorize this so much as understand how to use it to find maxima and minima. So let's actually look at a function and run through how you would do this. So you can see example 1, determine and classify any extrema of h of x, and we're given this algebraic function here. So you could plot this and you could kind of guess or estimate or approximate what the maxima and minima are. But at best you would have an approximation, and at worst you may miss some maxima and minima. So how do you know your window is right? How do you know there's no maxima and minima way out at a million or somewhere else? And so by applying this method where we look for all the critical points and then classify them, we know that we've done an exhaustive search and we know precisely where any of these maxima and minima are. So we're not approximating, we're finding exactly. All right. And this is also a very nice procedural way, so we're not just kind of guessing and checking, right? And that's generally a bad strategy, the brute force method. So let's go ahead and do this. And so we always want to start. You don't need to number this, but I like to just to organize things. So we'll start with always finding any critical points of the function. In this case, the function is called h of x, and I like to give myself a little reminder. A critical point is a place where the derivative is 0, so h prime is 0. And this is, if you just think about it for a second, this is a set of instructions. We need to find the derivative and set it equal to 0 and solve for x. So we can do all of those things at this point in the course. So the derivative of h is 16x cubed, so we're using the power rule here. And then the derivative, the second term is negative 25x, okay? And now we're going to set that equal to 0 and solve for x. This will give us, these values of x will be the critical points of x, places where the derivative is 0. So I'm factoring out an x because both terms have an x, and this just makes life easier. And so one of the solutions to this equation is when x is 0. That makes this true. The other solution is when, so we have two factors here, is when 16x squared minus 25 is 0. So we can set this equal to 0 and solve. So add 25 to both sides and divide by 16. And you'll get that x squared is 25/16. Now take a square root of both sides. Oh, try again. And we'll get the square root of 25/16. By exponent properties, this is equal to the square root of 25 over the square root of 16. So we end up with plus or minus. Remember, square roots have two roots, right? A positive and a negative. So we have two roots, plus and minus 5/4. So this tells us that h of x has critical points. At these three places. So negative 5/4, 0, and 5/4. All right, so great. That tells us where the function flattens out, but that doesn't tell us enough information to know if there are maxima or minima at any of these places. So this is where looking to the left and to the right of these critical points and checking the sign of the derivative, this is where we need to do that. So I would call this classifying. So classify any critical points. And I'm using this language any because it may be the case that there are no critical points. So if you're really lucky, then you'll do step 1. You won't find any critical points, and then you're done because a max or a min, at a max or a min, you have to have a critical point. So if there are no critical points, there can't be any max nor mins. All right. So classify any critical points. And the best way to organize this, I think, is to just sketch a quick table. So this is really quick to do, especially once you've done it a few times. So we're going to take the values of x that we have at our critical points, and we're going to leave a space to the left and the right because we want to check the behavior of the derivative to the left and the right of these critical points. So we have an extra space to the left and the right, and we'll choose test points there. Now at these critical points, by definition, the derivative is 0. So we already have the derivative values there. And then how do you choose test points is kind of the next question. And I like to just use the nearest integer to the left and to the right. So negative 5/4 is about negative, it's not about, it is negative 1.25. So negative 2 is a good choice there. And negative 1 to the right. If you don't like negative 1, for example, you could choose negative 1/2 or something like this. But just any point to the right of negative 5/4 and to the left of 0 is sufficient for this test. So moving on from 0 to 5/4, 1 would be a fine point, and then to the right of 5/4, 2 would work great. So, all right, so now we just need to plug these into the derivative. So let's pull up our calculator. So I have this emulator here, and you'll just go to your y equals, and you want to enter the derivative function and be careful not to enter the original function. So that's probably one of the most common mistakes that I see when I am grading tests for these types of problems. So if you enter the original function, then you'll just get completely wrong answers. So you can do this in two ways. The trace is probably they're probably equally as quick, but you should know both of them because they're just useful. So the trace button, just hit trace and it'll automatically plot it. And then as long as your window contains these critical points, then you can just enter, for example, negative 2 is our first value of x, and you can see y equals negative 78. So that tells us our derivative is negative at x equals negative 2. So we just put a negative number there and move on. So then you can do this at negative 1 and see we have a positive value and so on. So this is a really quick way to do this. Let me also show you, if you don't know how to do this with a table, this is really neat, especially for limits. This is useful. So go to table set. It's in yellow here, so that means you have to hit the second button and then click the window button, or tab, I guess. And then move down to the independent and change from auto to ask, and then go to the table. So that's over here on the far right. So hit the second graph button and that'll take you to your table. You'll see that it's blank, which is not normally the case. And this allows you to enter values. So this is really slick. And this is a nice sanity check because not only can you enter the test values, but it's a good idea maybe to enter the critical points, and this will be a sanity check that you did enter the right function, because at these critical points the value should be 0. So this will give you a nice check for your work that you did in fact find the correct critical points. So everything is looking good, and I like this too because now you can see all of the values in your table. So as we saw, at negative 2 it was a negative function value, and then at negative 1 positive, and then at 1 negative, and at 2 positive. So now we have all that information. So you can either use the table or the trace function. Both are very quick. So choose your favorite, and then we just need to interpret this information. So remember, the negative sign in the derivative tells us that the function's decreasing. So you can put the actual value. So I think at negative 2 we saw that the derivative was a negative 78. But the magnitude, the size of that negative value, the 78, that's not important here. We just care about the sign because the sign tells us the function's decreasing. So the 78 part of it just tells us how quickly. But in any case, it's decreasing. It flattens out, increasing, flattens out. And this is just the behavior of f that we're just quickly sketching in. Not f, but h. So from here, I like to do this because it's just a really quick way to interpret what you have at each critical point. So at this critical point, you can see we're tracing out a minima, and then at 0, x equals 0, the critical point is a maxima, and then another minima. Okay. So the last thing I always do is just state my results. So if anyone else is reading this, they can understand what the heck I'm trying to communicate. So h of x has a maxima at x equals 0 and a minima, and minima, not a, there's several. So just a quick sentence explaining your conclusions. So your work certainly doesn't have to be just like this, but this is, I think, most people like to use this, and it's a nice way to organize things. So you can kind of chunk this into smaller problems in this way. Okay, so that's the general idea of how to use the first derivative test to find and classify extrema of a function. So these problems are for practice. So I will fill in these problems right now. And what I want you to do is go ahead and try these on your own. So go ahead and pause the video, and in an instant they'll be finished for you when you unpause, and you can see how you did. All right, so hopefully things kind of made sense for you, but go ahead and check these solutions out. And again, these annotated notes are available at all times, so you can always go back and look at these on your own separately. And I will put a link to the annotated notes in the bottom of this video as well. So, and these questions, if you do have any questions that you want to clarify, any parts of the question, then, or if you think there's an error or anything like that, this would be a good thing to ask your instructor about during office hours. Okay, so let's look at the next example, and this is actually the same thing, but this looks a little different. So the first time you see a problem like this, you may be caught off guard or not be certain how to approach it. So the key here, so we're given a function just like many problems, and there's a context here. The context is that we have this function that models a business's expense. The units of the function are in dollars. Always be paying attention to units in general, because you may be asked to interpret your answers. So what is this number? We did some calculation and we found an answer. What the heck does it mean, right? So, but in any case, this is a function of the business's expense in dollars based on the input of P employees. So the input is a number of employees, and this spits out the business's expense. Just taking a quick look at the function, I see that it's cubic. Intuitively, we may think, oh, well, a business's expense should be linear, and so just be careful to be cognizant of any intuitions you might have that might lead you astray. So this is nonlinear, so it's not true that as we add more employees necessarily that the business's expense will go up. In any case, let's see what this question's asking. It's asking us to two things, actually: to determine the number of employees that will minimize the business's expense, and then what is that minimized business expense. So whenever you see these keywords, minimize, maximize, or even optimize, I guess, then that's a clue to that we want to use the first derivative test. So we're going to look for, in this case, minima. But in general, just use the first derivative test, and that will flush out any maxima or minima of the function, and then you can sort out what you need. All right. So that means we're just going to follow the exact same procedure. All right. So again, find any critical point. So you should be a pro at this if you did the problems above. So again, I would definitely just pause this and work ahead and see how you did. But let's continue. Find any critical points. Of our function, in this case c of p, a critical point is a place where the derivative is 0. That's a definition. So that's also a set of instructions for us. So we take the derivative. We should get 3p squared minus 18p minus 48. The derivative of 552 is a constant, so that derivative is 0. So if you're wondering where the heck did that term go, it didn't go anywhere. Its derivative is 0. So if you want to put plus 0, you can, but that's usually we don't, right? It's just kind of redundant. So each of the, I'm noticing you can just immediately solve this without factoring anything when you set it equal to 0, because you can just use the quadratic equation. But one thing I notice is that each of these terms has a factor of 3. So I factor that 3 out and divide both sides by 3, and that cleans things up a bit. So in general, though, of course, you can just solve these in any way that's algebraically correct, and there are many, many ways to do this. So just choose your favorite that will increase your chances or reduce your chances of error. So, all right, so from here, I can see that this factors into p plus 2, the quantity p plus 2 times the quantity p minus 8, okay? If you don't see the factorization, no big deal, just use the quadratic equation, all right? But what this tells us is that the function has 2 critical points. At -2 and 8. Now, whenever you're doing a context problem, especially when you're using the first derivative test, we're gonna have to classify these critical points, right? And so you can save yourself some grief by just taking a second and thinking about what these values of P are. These are numbers of people, so we can't have a negative amount of employees, right? So this critical point at P equals -2 is non-physical. It's not possible, right? So we won't classify this point because it's irrelevant. So I don't really care if it's a max or a min, it's not possible, so it's erroneous. So we won't classify this point. So we'll just save a little bit of time. Okay, and so we just have one left, and so if you've done any math problem, then you probably think, well, this is what they're leading me to. This must be the one. There's only one. But we should always be rigorous and justify. So let's classify this critical point and be sure that it does minimize, not maximize or neither or something like this. So again, we're just going to make a table with the derivative, and we're going to include our critical point and a test value to the left and the right. The nearest integer to the left and the right is what I would suggest, but again, it's not too vital that you choose the nearest integer, just any value to the left and to the right, or in between critical points. So entering this into the calculator, just again go to the y equals, enter the function, and then we can go ahead and just use that trace feature or the table. If you go to the table, you'll probably have the values from the previous problem, so you may need to change those. And so let's see here. So this may happen to you. So I went ahead just to show you what's going on, and I entered my 3 values. So 8 is my critical point, 7, 8, 9. Now if I wasn't being careful and I didn't check my critical point, then I would have probably went ahead and had an error and got the problem wrong. So at 8, what I found was that my derivative was 0. That was a critical point. But when I plug this into my function, I see that I'm getting a positive number, 7,104. So that's a flag for me to check my work to make sure that I did get the correct critical point. But before I do that, I should really check my function and make sure I entered it right. Now, if you look at this, it may look like it's okay, but there's a subtle but important error that I made. So if you look at the last term, it looks like I subtracted 48, but I put minus 48, and the calculator treats those as 2 different things. So you need to make sure you hit that minus and not the negative sign when you're entering these. It won't throw an error, as you saw, and it will change your calculation. So now you can see we go back, and sure enough, we have the little sanity check that at our critical point, this function is spitting out 0 like it should. And so now I see that at 7, the value is negative, and at 33, it's positive. So we'll go ahead and fill that in and interpret that result. So negative and then positive. And so this means that our business expense was decreasing, flattens out, and then increasing. So this means it's minimized at 8 employees, all right? All right, so the business expense is minimized at 8 employees. And then the minimized expense is the second question. And so that is going to be the value of the function, because the function gives us the business expense. So the minimized expense will be the expense at 8. And so for this, we just need to plug it into our code. So go ahead and plug 8 into the original function, and you should get $104. All right. So that wraps up this problem. So the last thing that we'll look at are a couple of plots just to sort out what this means graphically. So the first one is just to make sure you can identify these things on the original function. So it says that given these plots at each critical point, classify them as a max, a min, or neither. So the difficult part here is probably not finding the max or mins, but just making sure you have that connection to the critical point. So critical points are places where the derivative is 0, and so these look like places where the function flattens out. So you can draw tangent lines to see those points. So for this first function, g of t, you'll see this happening at x equals -1.5, x equals about 1/2, and then 3.5. So just write that as a list. And then the classification is pretty clear. This is something we all understood before we knew any calculus. So these are just the standard maxima and minima. Okay. So g of t has a maxima at about x equals 0.5 and minima at -1.5 and 3.5. All right, so that's it. That's pretty standard. That, again, just making the connection between what do critical points look like on the original function versus what do they look like on the derivatives. That's what we'll do with the next question. So I have this magic pen. I'm gonna apply to part B, so I don't have to do the work, but you should pause it and try part B on your own. So let's give this a try. Okay, so you can check it out. This just has one critical point at roughly x equals 5. So you can see the function flattens out there by sketching that tangent line. So, and you can also see that this is neither a max nor a min. All right. So now let's take a quick look at what this looks like in terms of the derivative. So now the same question, find any critical points of the original function and then classify them as a max, min, or neither. So if we look at part A, what we're trying to find out is our critical points of P and classify those as max, min, or neither. So your intuition so your eye may be drawn to this place at about -1.5 because that looks like a minima, right? And it is a minima, but it's a minima of P prime, right? That's the plot that we have. So be careful because that's not a minima of the function P, it's the minima of the function P prime. So how do we find minima of P given P prime? Well, we follow that test, right? The test says that we should find critical points, and those are places where the derivative is 0. So we have the derivative plot, so look for places where the height is 0. So the critical points of P then will be at -5 and 2. Again, because critical points of P are places where P prime is 0. So those are the critical points, and to classify those critical points, we can do the same thing that we've always done. So we're just actually applying that first derivative test, just classifying from there. So at these critical points, we know that P prime is 0. Take a point to the left of the first critical point, like -6, and look at the function. It's above the x-axis, so it's positive. And then take a point to the right of this critical point, -5, and to the left of 2. It doesn't matter what point you choose. Let's choose -2. And look, and we see that the derivative is negative. It's below the x-axis. So we're not looking at increasing, decreasing information. We're just looking at height information. And then take another test point, let's say 3, which is to the right of 2. And so we see positive. So now this tells us the behavior of P, tells us P is increasing, flatten out, decreasing, flattens out, increasing. So we can then classify these critical points. We see that P has a maxima at x equals -5 and a minima at x equals 2. You can actually gain a deeper insight than just this problem by just thinking about this for a second. So this means that anytime you have a derivative function that slices through in this direction, right? So the derivative changes from positive to negative, then you'll always, always, always have a maxima at that critical point. And anytime you see the derivative have this behavior where it cuts through the x-axis and the derivative changes sign from negative to positive, you'll always have a minima at that critical point. So if you were given, let's just scoot over to the margin here. Doesn't matter how wild and crazy the derivative function looks, just choose your favorite. Let's just call this k prime. So if you understand that idea that the way that you cut through the axis tells you whether you have a max or a min on the derivative plot, then you can very quickly identify the critical points and whether you have a max or a min. And I want to change this actually, just to make it a little bit more interesting. Okay. So again, just paying attention to how things are slicing through, you can classify these as max or min or neither. So here, the derivative is 0, and the way that the derivative cuts through x equals -1 is that it changes from a negative sign to a positive sign, right? To the left of -1 it's below, and to the right it's above. So this tells us that we were decreasing and then we were increasing. So that sweeps out a minima. Notice we have that same pattern at x equals 3. So we have a minima at x equals 1 and a -1 and x equals 3 of k of x. Similarly, you can probably guess what this one's going to be. The derivative changed from positive sign to negative sign as it cut through at x equals -2. So this would be a maxima of k of x because the function k was increasing and then decreasing. So think about what's happening. If you're increasing then decreasing, you're tracing out a downward facing looking parabola, okay, in that area. Now there's one more critical point at x equals 4. So that's what I wanted to, that's why I redrew this sketch, because I wanted to include this. So this is the third case you might see where you have a critical point here, but neither a max nor a min. And that's because the derivative has the same sign on both sides. So this is a critical point, but neither a max nor a min. Okay, so think about that example. Hopefully that helps you sort this out. But the idea is anytime you see a derivative plot, you can actually almost instantaneously, if you understand this idea, you can immediately find the critical points and you can classify whether they're max, min, or neither. So this is actually the quickest, this is the problem you want to get because it's very quick. There's no algebra involved and you just need to interpret the diagram. So go ahead and try part B on your own, and as before, I'm going to use my magic pen and I'll provide that answer, and that will end this lecture, so let me include that.